In this video, I'll try and explain some of the basic kinematic equations under uniform acceleration. For all these cases, we'll look at objects which travel with uniform acceleration. Objects can also definitely travel in with varying acceleration, which is the case most of the occasions. But for these simple kinematic equations, we'll look at objects with uniform acceleration. We already know one such equation is v equals u plus at, which means the final velocity of an object is the initial velocity u plus whatever it has gained over time t in the form of the velocity added by acceleration. Acceleration adds to the initial velocity over time, and if it's adding for a longer time, then obviously a times t is higher and the initial velocity gets added by a higher quantity to get a bigger final velocity. So this is one equation. Now let us look at the relationship between velocity, time and displacement again. We know that velocity is nothing but the rate of change of displacement, which is velocity equals displacement denoted by s divided by t. If we have a plot for the same, which means the x-axis is time and the y-axis is velocity, and we plot the line velocity for an object traveling with constant velocity as shown by the black solid line here, then let's say it travels for time interval t. Then this shape, that is this black line, is parallel to the time axis, and so we can see that this is a rectangle. Okay, so now this shaded area of the rectangle will be, if this is 0, p minus 0 is v, p minus 0 is t, length times breadth is vt. We also know by rearranging this equation that displacement is velocity multiplied by time. So here we see a Vt, here we see a Vt, which means from this picture, this area is Vt, but we also know displacement is Vt, which means the area shaded here is the displacement of the object over time t. So we can, in other words, say that when we plot velocity versus time like this, the area under the curve, the area under the line is nothing but displacement. We can also check this by taking the units of velocity is meter per second multiplied by units of time is second. So this gets cancelled and we get meter, which is the unit for displacement. Now let us use this to derive a couple of more equations, kinematic equations. Let's look at this particular plot. Here at time t equals 0, the object is already having an initial velocity u, starts from here, which means when we see the object, it's already moving with the velocity u, and it is under uniform acceleration, which means constantly velocity is being added at same time intervals, the same amount of velocity, and after time t at this instant, it has a velocity v. Now we know that the area under this black solid line is denoting displacement. That means this complete area denotes displacement. Let's divide the area into two parts, two known geometrical figures. One is a rectangle, one you can see on top is the triangle. So let me shade this triangle this way, and this is the rectangle. Now we know the area under this black solid line formed with this closed figure, which we have formed here, is nothing but displacement. We have already seen that here. How do we calculate the area of this particular figure? We can calculate the area of this triangle, we can calculate the area of this rectangle and add them up, which will give us displacement s. Let's try and figure it out. What is the area of this rectangle, of this triangle? By symmetry, you can see that the area of this triangle is half of the area of the top rectangle here. So one dimension of the rectangle is v minus u here, and this whole thing is nothing but t. You can say the length is t here. So t times v minus u times t is the area of the rectangle on the top, but this black solid line is the diagonal which splits the rectangle into two equal halves. So half of this area of this rectangle is the area of the shaded triangle figure here. V minus u times t divided by 2, or half of v minus u times t. And what is the area of this rectangle at the bottom here? It is nothing but u minus 0, which is nothing but u is the breadth of the rectangle, and the length we can say is t minus 0, which is t. So one dimension is u, the other is t. Area of the rectangle is length times breadth, which is ut. So let's add these two to get the area of the closed figure, or area under the line, which is nothing but displacement. So it is ut, initial velocity, times t, plus we can rewrite this as half v minus u times t. So we are adding both. Now this can be written as ut plus, from this equation we know that b minus u is nothing but at. I'm just bringing u to the left hand side of the equation. V minus u is at. So we can rewrite this as, this v minus u becomes at. So half at times t. So we get an equation which says s equals ut plus half a times t square. Now this is another equation, kinematic equation, which we can call equation number 2. So we have two equations now, equation 1 and 2. Now let's look at another concept to get one more common equation, the third equation of kinematics. So we know here that under uniform acceleration, all these are of course uniform acceleration. The average velocity only under uniform acceleration, this is important. If the acceleration is varying, this cannot be true, need not be true. So under uniform acceleration, we can always say that the average velocity, which is denoted by the bar on top, equals initial velocity plus final velocity divided by 2, the average of the initial and final velocities. So it can be intuitively, you can see that if an object is traveling at 2 meter per second, the first time interval, and at regular time, the acceleration is, let's say, 2 meter per second square. Initially it's traveling at 2 meter per second, then next second it's 4 meter per second, then 6, then 8. So if we take the average of this initial plus final, 8 plus 2 by 2, then the average will be 5, which intuitively makes sense. 5 is sort of closer to 4 and 2 initially, and it's the average of all these. So, but let's say an object has always been traveling at 2 meter per second, and in that last instant, it suddenly accelerates to 10 meter per second. It's always having a constant velocity. There is zero acceleration. The last second, it just accelerates away to rapidly to from 2 to 10 meter per second, and a huge acceleration. In this case, if I take initial velocity plus final velocity by 2, which is 10 plus 2 by 2, the average will be 6 meter per second, which doesn't make sense intuitively, because the object has always been moving at 2, only in the last second it became 10. So I cannot intuitively say that it's on an average it's moved at 6 meter per second. Let's assume that instead of 3 instances, this is 10 instances. Then there would be a lot of 2's before this. For that object, if I say 2 plus 10 by 2 is 6 meter per second, it would not make sense, because the object has 95% of the time it's been moving with 2 meter per second only. So that's just to, not exactly the case, but to intuitively explain why we can do this only for uniform acceleration. So if the acceleration is uniform, we can constant velocity, the same velocity is added every second to the object. So we can, for the entire time interval, we can say initial velocity plus final velocity by 2, which is the average of initial and final velocities, is u plus v by 2. This is true for uniform acceleration. Now let us take this case and try to form an equation. Now if initial velocity plus final velocity by 2 is the average velocity, then we can say that, so the displacement we know from here is velocity multiplied by time. So in this case we can say displacement is average velocity multiplied by time. What is average velocity? Average velocity is u plus v by 2 from this particular equation, from here. So we can say it is u plus v by 2 times t. But we also know from the first equation here that u, we can say that t is nothing but v minus u by a. So we can say that v minus u by a equals t. I'm just rearranging this. Taking u to the left hand side, it becomes v minus u, and that divided by a gives you t. So let's substitute this value of t here and see what happens. V minus u, this equals u plus v by 2 times v minus u by a. So which is nothing but this particular thing is being written there. Now this will again result in, what is u plus v times v minus u? This is nothing but v plus u times v minus u, which we know by the identity that mathematically a plus b times a minus b is a square minus b square. So we can write this as v plus u times v minus u is v square minus u square by 2a. This is s. So this implies that v square minus u square is 2as by cross multiply. So this is another equation that we are getting, which we can call as equation number 3. So there are 3 equations we get. V equals u plus at, s equals ut plus half at square, v square minus u square is 2as. So these are the 3 equations for kinematics which we have seen. Thank you.